All right, so transformations, just like any other function, log functions get transformed. I don't know if you did this last year or not. Did you talk about transformations with log functions, shifting left, shifting right? You did them with most functions, so I don't know why you would leave logs out, other than maybe it doesn't show up on the regions that much. The thing is, on the regions, when they say, oh, graph this, by the way, you can just type it into your calculator and use your table, which is what most people do. So you don't really have to fully internalize this, but now, given that you don't have a calculator, you're going to have to fully internalize that. All right, so for the record, the parent graph, when your base is 4, so I'm going to rewrite this as y equals log base 4 of x. And then if you're kind of translating that to a language that's more familiar, 4 to the y equals x. And then if you were making a table of values, usually with most functions, you pick the x coordinate and you get the y coordinate. This is a little bit different because if you look at the rearranged version, it would be most helpful to know the y coordinate first. So if you pick a y coordinate of 0, 4 to the 0 power is 1. A y coordinate of 1, 4 to the first power is 4. A y coordinate of 2, so 4 to the second power gives you 16. You actually can pick a negative 1 if you want. 4 to the negative first power is 4 to the negative first, 1/4, good. And negative second power, 4 to the negative second power is 1/16. So if I cross that out now and go back and think about my parent graph, these are all the points on it, and you'll see some of the features of a log function come up. So if you plot 1, 0, 4, 1, 16, 2 is going to be impossible to do, but it does give you a little feel for how flat this gets, how quickly it gets flat. Negative 1/4, negative 1, 1/16, negative 2, and really you get infinitely close to 0. You can see that happening because if I plugged in a y of negative 3, I would get 1/64, and so 1/64 is barely off of the y-axis, and you get obviously infinitely close to the y-axis as your y coordinates get more and more negative. So you can see the domain of log base 4 of x having to be greater than 0. You can obviously see that there's no limitation to what y values you can plug in, so your range is undefined, or unrestricted, I should say. Your range is all real numbers. And so there's our parent graph. And so if we were to sketch this, what transformation occurs first, Mackenzie? Horizontal or vertical? Oh, this is funny. I realized this in Algebra 2. Horizontal and vertical aren't as obvious to us as I would think that they are. I think I confuse a lot of my Algebra 2 kids when I say horizontal. They don't know what that means. Do you guys know what that means? But you're not very confident. Your gut is right. It is horizontal is all things left and right. Right? Vertical are all things up and down. Yes? Some of you are like, how do people not know that? But shockingly in Algebra 2, I'm starting to realize that that's what confuses people. Not like they'll get the left or right part right, but they might say vertical shift left. And I'm like, wait a minute, that doesn't make any sense, right? So horizontal is all things left and right. So we always start with our horizontal movements, Mackenzie, and that's whatever happens inside. So this negative is a horizontal what? If I'm reflecting horizontally, which axis did I just jump over the y? followed by your vertical shift up 3 that you mentioned. So just 2 transformations. I can take, mostly my critical points and do these all at once. So this will flip over here and then up 3. This will flip over here and then up 3. This will flip over here and then up 3. And so it goes. So because we're now looking at it, we can say what the domain is. This is part B. What is the domain, would you say, Morgan? Yeah, of the new one. To what? Just this graph. This graph does not go all the way to infinity, no. The x coordinates, the domain, go from negative infinity up until 0, parenthesis or bracket. Correct. And your range is still all real numbers. Oh, shoot. I'm doing this one. Sorry, I didn't realize that was for a different problem. Sorry, write this up here. So that we got that because we took the time to graph it. But if we didn't take the time to graph it, couple things. You can only take the log of a what? What kinds of numbers? The only numbers you're allowed to take the logs of are positive. So whatever this is that you're taking the log of, this negative x in this case, has to be greater than 0. And so if I'm going to solve that for x, what do I have to do to both sides? Divide by -1. And if I'm solving an inequality and I divide by a negative, I have to remember to flip the sign, and that's where your domain comes up. X has to be less than 0. So we can do this algebraically is my point. You don't have to pause and graph every time. And then your range for a log function is always all real numbers. Unless they restrict the domain and say what is the range when you're only looking at a domain from 5 to 7, then you'd have to look at it. But if it's just the full function without any restrictions, then the range is always unlimited. Okay? So you don't have to think much about that. So just like with a radical, if you were looking for the domain of a radical, whatever's underneath, you set greater than or equal to 0. If it's a fraction, whatever's underneath, you say cannot equal 0. And now for logs, whatever you're taking the log of has to be greater than 0. Okay? That's the algebraic approach for finding domains. And these now are our 3 situations that have limited domains. Okay, so on B, if I'm following that algebraic approach, this x plus 3 has to be greater than 0. So x is greater than -3. That's your domain. Your range, because I told you, is always all real numbers. Any questions? Okay, common logs. I don't know if you remember this or not, but logs that have no base written, you have to have a base of 10. Do you remember that? So your calculator, if you just hit log of something, log of 50, that is going to process a log base 10 of 50. So 10 to what power would you say gives you 50? Guesstimate what the value would be. Between what two integers? This is fun because you're going to have to do some estimating since you don't have a calculator. Log of 50 is asking you 10 to what power gives you 50. Is it 10 to the 0 power? No. Is it 10 to the first power? Is that 10 to the first power? Is that too big or too small? Too small. Is it 10 to the second power? And that's too big. So it's going to be somewhere between 1 and 2, right? That's really the best you guys can do. Now we find out it's 1 point whatever. Okie doke. Okay, so some that you'll have to be able to do is like log of 1,000. That one you should be able to get exact. 10 to what power gives you 1,000? Olivia? 10 squared? 3. 10 squared is 100, because 100 has 2 zeros. 10 cubed is 1,000, because that has 3 zeros. So this would equal 3. Just remember that if you don't see a base, it's 10. What do we have here? The percentage of adult height attained by a boy who is X years old can be modeled by, well, this will be fun. This is what we're going to use to predict my 3.5-year-old's adult height. I'll let you know in 20 years if it's accurate. So, here's the function. X plus, I hole punched it out. Don't worry. I steal these from the book. I can find it. X plus 1. So I can use this function to predict the adult height attained by a boy who is X years old. Oh, the percentage rather. The percentage of his adult height. So this won't give me the adult height. If I plug in for a 10-year-old boy, approximately what percentage of his adult height has a boy attained by age 10? I would do f of 10. Now, I think I mentioned yesterday that on this test there will be a calculator section because there are some certain most log applications aren't going to work out nicely. So if we want to use log information or a function that uses logs to model what's going on, you're going to probably need a calculator. So if I type this in, 29 plus 48.8 log 11. This tells me that by 10 years old, a boy typically is 79.8% of his adult height. Does this make sense? So if I set a 10, how tall is a 10-year-old? Give me a random guesstimate. Does anybody have a 10-year-old brother? Nobody? 10-year-old cousin? All right, so we'll pretend for 11, we'll pretend if she's a boy, she'd be 5 feet even. Who cares? Okay, so let's pretend there's a 10-year-old boy who is 5 feet tall. What does this information tell us he will be when he's an adult, when he's fully grown? So let's say when he's 25 years old, right? So if he's 5 feet tall, is this, I'm going to change that to inches. Okay. So essentially what this model is telling us is that 60 inches is 79.8% of his adult height. So this is basic algebra 1 percentage information. What then, take a moment, get your calculators out, take a moment to figure out what his predicted adult height would be. Bailey, what'd you get? What?
I don't know.
Do you remember percent over 100 equals is over of? They never taught you that way. How did they teach you to do percentages? Okay, so percentages are nothing more than a direct proportion. Whatever the percentage is over 100% is equal to the part over the whole. Do you remember that? Percent over 100 equals part over whole, maybe? Maybe they phrase.
But I can probably do it now.
Okay, so your percent, 79.8 over 100%. The reason, I was taught is over of because the is usually the part of the whole, right? So a lot of the language, if you read them, will have the word is and out of whatever. And so we just plugged in based on that. But if you go part over whole, this 60 inches is the part of his adult height. And your X, what you're looking for is his full adult height. So you just cross multiply. So apparently, this little guy will be that many inches divided by 12 inches will be that many feet. What's 0.265? How many inches? 0.265 of a foot is how many additional inches? Aiden? 3-ish, right. 0.265 of a foot is 0.265 of 12 inches, gives you an approximate 6'3" guy. I don't know if this is accurate. So this would be my child, who's 3.75 years old, almost to the day. November 4th, he'll be 3/4 of the way to his 4th birthday. So we're going to go with it. If we really want to be funny, we could put like 3.74. And I'm guesstimating. I use my ruler, like kind of guesstimate how tall he was. I think he's about 41 inches. So right now, that's 62% of his adult height. So 62% out of 100% is 41 inches out of X inches. 66 inches. That's not good. Oh. Maybe 41 was an underestimate. Now I got to find out tomorrow. 5'6". I'm taller than 5'6". Uh-oh. How about you guys? You're how old, John? 17 point what? Are you 17 and a half? When's your birthday? Oh, May 9th. Duh. So you're almost, add 6 months to that. That would be November 9th. So you're just shy of 17 and a half. You can do this for yourself if you'd like. Not you, Mitch. You're not allowed. Because you're too tall. You'd be up there with, this might put you up there with our friend Robert. You are? Well, let's see. So what this tells us, well, I bet this is a little off. What this tells us is that by 17 and a half, you're about 91%, we'll say, of your adult height. So you're pretty much done growing. So, John, how tall are you? 6'4"? 6 foot. I was going to say, come on. So 6 foot, 6 times 12, 72 inches out of X inches. So 7,200 divided by 91. So that says you're going to be 79 inches tall, which means you're going to be 6'7". That's not true. I don't think this, it's obviously no model is perfect, but how do they come up with a model like this? They grab data, they throw it on a scatter plot, and they come up with it. It would have to be a pretty, let's see, if you were to collect data to try to make a scatter plot of this, you would need to collect ages and what percent of their adult height they truly are at that age, which means you'd have to find a 3-year-old, and then you'd have to follow up with that 3-year-old when he's an adult and see, say, what was his, obviously he's 3 years old, you'd have to collect his height then, and you'd have to collect his height as an adult, and you'd have to figure out what percentage he actually was, right? And then you'd have a point. So this would take a while to collect the data. But that's how you do it, and then you come up with a model. I'm sure your thing must look something like this. That's what a log graph looks like, right? Which makes sense because the older you get, the more this is flattening and not growing. The log model is not exactly ideal though, because even though it's pretty flat, this goes under the assumption that it's always slightly increasing, which we know is not true about height. In fact, eventually your height shrinks. So it might be a better model only for a certain amount of time. You really can't use it once you get up to full-grown people. But anyway, interesting. Moving right along. Natural logs. What's the base of a natural log? E, this weird number E. So log base E of X is the natural log of E. But they're still logs. So when you go to find the domain, whatever you're taking the log of has to be greater than 0. Add x to both sides. X has to be less than 3. On the h of x function, this one's funny. Because the question would become, are we squaring that x minus 3 first and then taking the log? Or do we is it squaring the entire log of x minus 3? I almost don't know. I'd have to, my gut says, because the question would come down to where does logs fall in order of operations, right? I think notationally, if they wanted to square the entire log, they would have to do that, to be honest with you. Does that make sense? If you wanted to square the entire log, you would put it in brackets and then square it on the outside. So, given that it's written like this, exponents comes first, parentheses, exponents. It's funny though, because logs in a way are exponents. So, anyway, I'm telling you, that bracket would have to be there if they were going to square the whole thing. So they're essentially squaring this first. So how is this going to affect our domain? How would we, what numbers is x allowed to be? Anything but 3. So initially you're like, okay, well it's going to be anything because anything squared is positive, so you're good. But that's not true. Anything squared is not positive, right? What number squared is not positive? What'd you say? Not a real number. Sorry. I like you trying to get into a special thing here, but what real number, when you square it, is not positive? 0. And that's where Connor came up with 3. Because if x is 3, 3 minus 3 is 0, 0 squared is 0, you can't take the log of 0. So x can be any real number except 3. And then your basic log properties for natural logs are going to be a lot of the same. They are the same as what we did yesterday, but we'll just think of them a little bit differently. The log of 1 is always what? 0. Right? The base of e to what power would give you 1? This is log base e of e. What's that? Log base 5 of 5. Log base 7 of 7. Log base e of e is 1. This is log base e of e to the x. What's that? Just x. And this last one is e to the log base e of x. What's that? X. Those sort of cancel, just like those sort of cancel. All right, last word problem. When the outside air temperature is anywhere from 72 to 96, the temp in an enclosed vehicle climbs by 43 degrees in the first hour. This function here models the temperature increase after x minutes. Find the temperature increase to the nearest degree after 50 minutes. So if I just plug in a 50, again, it's a calculator question. So I'm going to plot this. When I plot this, my x-coordinate stands for minutes, correct? So I'm going from 0 to 60 minutes to cover my first hour. My y-coordinate stands for the number of degrees that it rises, which I know is 43 in 1 hour. So I'm going from 0 to 43. So what this log model tells us essentially is that in those first few minutes that a car is parked on a hot day, the temperature increases very quickly. Like that's like the greenhouse effect or something, right? Right? I don't know. Connor's agreeing with me, so I'm saying yes. That's what my gut tells me. There's something involved with the greenhouse effect. So it increases really quickly, and then it almost gets to its maximum temperature and increases very slowly for the rest of the day. So if I did this over like a 6-hour period, oh boy, I have to go up higher than 43 degrees. Over a 6-hour period, it essentially really stops increasing in temperature because it's reached its maximum until the outside temperature starts cooling. Anywho, what do we get for F of 50? Or didn't you? I got it. 40.8, which is almost that full 43 degrees.